Welcome to episode 26 of 100 Days of Data. I'm Jonas, an AI professor here to explore the foundations of data and AI with you.
And I, Amy, an AI consultant, excited to bring these concepts to life with stories and practical insights. Glad you're joining us.
Like training a dog, but digital.
That's a great way to kick off today's episode on reinforcement learning, where machines learn from rewards and penalties just like pets do.
Exactly. Reinforcement learning, or RL, is one of the main ways AI systems learn to make decisions. Unlike traditional teaching methods where you feed lots of labeled examples, RL is about learning through interaction with an environment. The system, what we call an agent, takes actions, observes results, and adjusts behavior based on rewards or penalties.
So it's not just about showing the AI what's right or wrong up front, it's more like trial and error, but smart trial and error. Think of a dog learning to sit. You don't tell it the exact movements. You reward it when it sits and ignore or gently correct it when it doesn't. Over time, the dog figures it out.
That analogy is spot on. To understand it better, let's break down the core components in RL. First, we have the agent, which is the learner or decision maker. Second, the environment, the world the agent interacts with. Then there's a state, which represents the current situation the agent finds itself in. Finally, actions are the choices the agent makes, and rewards are the feedback signals guiding it.
Right, and each action leads to a new state, creating a cycle. State, action, reward, new state. The agent's goal is to maximize its cumulative reward over time, so the reward acts like a scorecard, telling the agent how well it's doing.
Historically, this idea links back to theories from psychology and behavioral neuroscience, like operant conditioning. B.F. Skinner famously showed how animals learn behaviors via rewards and punishments. RL brings these ideas into machine learning, letting algorithms learn from experience rather than just data.
This is where RL stands apart from supervised learning, which you hear about often. In supervised learning, you have clear right or wrong answers to train on, but RL is closer to real-world decision-making. There aren't always correct answers given up front. Instead, the AI figures out a strategy or policy based on feedback it receives as it acts.
That's a key point. The policy is effectively a mapping from states to actions, how the agent decides what to do next. Over time, the agent refines this policy to maximize rewards. RL also incorporates the concept of exploration versus exploitation. Should the agent try new actions to discover better rewards, or stick with what it knows works well?
In practice, balancing exploration and exploitation can be tricky. I've seen this in retail when AI helps with personalized marketing campaigns. The system might test new offers, explore, versus sticking to those known to perform well. Too much exploring wastes resources. Too much exploiting risks missing better opportunities.
Exactly. Another core concept is the value function, which estimates the expected future rewards from a given state. It helps the agent evaluate how promising a situation is even before actions are taken. Then there are different RL algorithms like Q-learning and policy gradients that learn these value functions or policies in various ways.
Speaking of algorithms, one breakthrough was applying RL to games. Remember AlphaGo? It famously beat the human world champion in Go. That was a big milestone because Go has an incredibly complex state space. AlphaGo used RL to improve itself by playing millions of games, learning what moves led to victories.
Yes, that was a thunderous demonstration of RL's potential. Game environments are well defined with clear rules and rewards, which make them ideal learning grounds. But RL is now breaking into less structured real-world domains too. For example, robotics.
In the automotive industry, RL helps with autonomous driving. Self-driving cars need to decide when to accelerate, brake, or change lanes. They learn from simulations, getting rewarded when they drive safely and efficiently, and penalized for risky behavior. This approach enables vehicles to adapt to complex and unpredictable environments.
That's an important application. Another one is in healthcare, specifically personalized treatment plans. RL algorithms can learn the best sequence of treatments for patients by analyzing outcomes and adapting recommendations over time, balancing risks and benefits.
And in finance, RL powers algorithmic trading strategies that continuously adjust to market conditions, aiming for higher returns or lower risks. It's a dynamic setting where the environment is constantly changing, making RL's adaptive learning especially valuable.
It's exciting to see RL's impact growing, but it's worth noting the challenges. RL requires a lot of data or experience to learn effectively, which can be costly. Plus, designing the right reward signals is tricky. Poorly designed rewards can lead the agent to weird or unintended behaviors, what we call reward hacking.
Absolutely. I've seen projects stall because the reward system was too simplistic. For instance, in a customer service chatbot, if you only reward it for quick responses, it might rush answers at the expense of quality.
That highlights a key design skill in RL, crafting reward functions that align with desired business goals. It's as much art as science.
Also, there's always the trade-off between safety and exploration. In some domains like healthcare or finance, experimenting blindly isn't possible. So organizations use simulations or constrained learning to keep things safe while still gaining experience.
Exactly. To sum up, RL teaches AI agents to learn by doing, making decisions, getting feedback, and improving over time. It's inspired by natural learning processes and guided by concepts like agents, states, actions, rewards, and policies.
And from my side, it shows up in practical AI systems today, from self-driving cars to recommendation engines to robotic process automation. The business impact comes in automating complex decisions, adapting to changing environments, and personalizing experiences in ways classic approaches can't match.
So, your key takeaway, Amy?
RL turns AI into an active learner, not just a passive processor of data. It's powerful, but demands careful design and lots of experimentation to get right.
And mine is, RL combines trial and error learning with mathematical frameworks to guide agents toward optimal behavior across diverse scenarios.
Next episode, we're taking a deep dive into neural networks, the building blocks behind many AI advances.
If you're enjoying this, please like or rate us 5 stars in your podcast app. Leave us your questions or comments. We might feature them in future episodes.
Until tomorrow, stay curious, stay data-driven.